Hello, everyone. I am Anil Godbole, Senior Data Center Product Planning and Marketing Manager at Intel. I'm going to present today about boosting AI workload performance using CPUs and CXL memory attached to the CPUs. Before we begin, I want to thank Memverge for giving me this opportunity to show why CPUs can still matter in the AI world today. I want to start by pointing a simple fact that there is too much pressure on CPU core counts to increase. And CPU manufacturers like Intel are, of course, keeping up with that. But the simple reason is that modern workloads have very big memory footprints. And these workloads cannot be satisfied by simply adding more memory. In the end, the demand for memory capacity and bandwidth in a server arises simply because there are multiple cores simultaneously crunching the workload. And today, of course, we will focus on the AI workloads. And to help increase the memory capacity, as we know, man invented CXL. As the graphic in the center shows, CXL allows one to augment a CPU's memory capacity beyond what it can do with its DRAM channels alone. Here we explain the value prop of CXL memory. The first use case on the left box is, of course, everyone is familiar with, everyone knows, okay, so we want to add more memory beyond what DRAM can allow us. And those are all the different workloads which can benefit. And the second box shows how CXL memory can also be used, besides adding capacity, can also be used to increase total memory bandwidth. And the third box shows how CXL memory can be used to reduce overall memory TCO. We are not going to focus so much on that, but I'll refer to it every now and then. And today we'll just focus on the second box. We will first explore how bandwidth is expanded using a technique called address interleaving. And later we will see how one can put this bandwidth for good AI use. But before we get fully underway, I want to show a quick slide to show that Intel remains fully committed to support CXL going ahead. With the recent launch of Xeon 6700/6500 series of processors, which are aimed primarily for enterprises, we now have completed the launch of all our 6th generation family of Xeons, previously codenamed Granite Rapids. This family offers a broad support for CXL in the sense that all CPU SKUs in this family offer CXL support. Now, here's a slide which shows the 4 possible configurations which the user can deploy using CXL memory. There are actually only two configurations, but on the left side, I'm showing what I call hardware control modes, meaning no OS or any middleware is needed here. It's simply the CPU BIOS which can configure this mode. And those 2 modes are for memory capacity expansion and memory bandwidth expansion. And on the right, we are showing the same modes, but now using software control techniques. Right? So this is where we use OS or middleware like Memory Machine from Memverge to do this steering. But today, we will focus on the bandwidth expansion modes, which are shown below. Of course, in these modes, the capacity is also increased, as I pointed out earlier. But some special configuration is done, like interleaved memory addressing to improve the bandwidth. We will begin with a slide to show the concept of address interleaving. It shows the Intel hardware control-based hetero interleaving mode. I want to explain how this method is to increase the memory bandwidth is something, actually this method to increase the memory bandwidth by address interleaving is something we have been using on RAID SSDs for all these years. So rather than store all the data for a given workload in a single DRAM channel, you can stripe that data across in chunks across multiple channels. So now when that data access takes place, it can be accessed 8 times faster if a CPU has 8 DRAM channels. Or it can be 12 times faster if it's a different processor like the GNR-AP or the Xeon 6900 series of processors. And then when you add CXL memory to the mix, then one can increase this interleave ratio even more. So a typical rule of thumb is a by 16 CXL channel has an equivalent bandwidth of 2 DDR5 channels. So if we employ 2 CXL channels out of the 4 available, effectively we are adding 4 more DRAM channels. And that's why we are showing that with DRAM alone, it's either 8-way or 12-way, but when CXL is added to the mix, we end up being either 12-way or 16-way. And here's an example of how an AI-related workload, AI workload which is related to the bone age assessment, got a performance good. We had performed this on our EMR system, ML Rapids, which is the 5th generation Xeons. And then this is one of the few AI inference workloads where there happens to be a good mix of reads and writes. And then let's look at the other approach to increase memory bandwidth, and that is the software base. This slide explains that. And this software technique or this software capability is now available through the Linux kernel beginning version 6.9. I want to acknowledge that our host, MemVerge, along with big contributions from Micron and Hynix, contributed this capability to Linux. Here, the memory physical pages are interleaved, or the whole virtual address, mapped into physical pages by the Linux page table, are interleaved between the main DRAM channels and the CXL channels. For simplicity, the graphic is showing only 2 nodes, one for main memory, which is the DRAM channels, and one for all CXL channels. But in practice, one can extend that to multiple NUMA nodes when DRAM channels are further split into sub-NUMA nodes, like some of the SNC modes we have on the Intel processors, sub-NUMA clustering modes. The granularity of interleaving here is 4 kilobytes, which is a Linux page size. This is in contrast to the hardware approach I showed earlier, which can do as low as 250 bytes. So some workloads may actually benefit because now the data needed can be gotten much faster because you're only getting 256 bytes from all the channels. You don't have to wait for the whole 4K to come in. But the more important benefit of the software approach is the ability to adjust the allocation ratio between the main memory NUMA node and the CXL node. The ratio of interleave, which I call M:2N in the graphic, is chosen based on the bandwidth ratio between the 2 memories or the NUMA nodes. And the bandwidth of one node, let's say one node is lower due to read-write access pattern. As we know, right, a DRAM channel is very good, highest bandwidth if you are doing all reads or all writes. But once you start doing read-write mix, then the bandwidth kind of goes down. And same thing can happen with CXL. When you do read-write mix, which is actually the opposite, because CXL is bidirectional channel, read and write, one benefits if you're doing both reads and write mix in the workload. But for read-intensive workloads, the CXL bandwidth comes lower. So it's no more one CXL channel is no more equivalent to 2 DDR5 channels. Anyway, whatever it is, right? The M:2N ratio selection can be used to offset this. So when the main memory bandwidth is higher, you choose M to be bigger than N and vice versa. Right? And there can also be a TCO play here. So imagine, let's say we had to use all 128 gigabyte DIMMs only using CPU memory, right? Before, let's say there was no CXL. to meet the workload demand. The workload needs so much footprint. So let's say it needs 1 terabyte footprint. Now, one can do the same thing between the main, by using CXL, one can now spread the memory between the DRAM and the CXL using, say, less expensive DIMMs like 64 gigabyte DIMMs. So as you can see, the total cost can now go down, but also you get a bandwidth boost. And now one might wonder why the higher latency CXL memory does not come in the way of performance when you interleave them with faster memory like DDR5. This is the question which people ask me the most. But the slide here shows why the net latency of a memory access is actually reduced when you do this address interleaving technique. As the blue curve shows, which is the DRAM-only curve, when multiple cores start doing memory accesses, the memory controllers becomes a bottleneck and starts queuing up the transactions. That shoots up the latency, the net latency to the requesting core, because some core is waiting on the transaction, but others are in the queue, right? So not because your DRAM got any slower, but simply because there's so much traffic congestion. But when CXL is added, CXL channels are added to the mix by using interleaving, there is more ways to spread this traffic across many, the more CXL channels, right? The other CXL channels, which won't be there if only DRAM was used. And that's why we see the flattening of the latency curve as shown by the orange curve. So yes, eventually even that will saturate if you keep on increasing the bandwidth. But at least you get a reprieve, right? From going in this graphic, going from 400 gigabytes to 600 gigabytes, the latency is still kept in check. Now, for the remaining part of my presentation, I'm going to cite a few examples of AI workloads which have benefited from the memory interleaving techniques, right? I just want to acknowledge the various contributions Intel has worked with so many IHVs. They have worked with us, partnered with us over the last few months at different shows to show off all the AI performance boosts we can get using CPUs and, of course, their memory. And keep in mind, there were no GPUs used for all these demos here, all these examples I'm showing. I won't have time to go through all the material, but I will leave all these slides here for reference. But I'll start by acknowledging the work we did with Micron. At the last supercomputing show in November, we were showing this RAG database acceleration demo. Quick slide on what that RAG database is. It's called FAISS. I believe it was contributed by Meta, but it has found good traction with a few cloud service providers. Not only they use it for AI RAG acceleration, they can also use it for search optimization. We were able to use this RAG database access time by up to 23% by using the memory interleaving technique. Next, I'm showing an example of a workload done by Intel's own internal performance team. Now, this time, we are showing the Redis vector database. Now, Redis, keep in mind, is an in-memory database, can be used to store all kinds of information, right? So, but when we use the Redis vector database, the database is quite sparse compared to a Redis document database, right? And at such times, the high bandwidth, which we get with memory interleaving, really helps. So once again, this is a popular one people use for RAG databases, and we are able to show a performance boost of up to 27%, 28%. And we had used our IHV Astera Labs CXL memory for this. And here's a contribution from our other IHV partner, namely Samsung. They showed off how yet another open source of RAG database called Milvus can be accelerated using this software memory weighted interleaving. They tried out many different ratios, and as you can see on the graphic side, and looks like 3:1 ratio was the best and provided a 17% boost. And now moving a little bit away from the RAG database acceleration, here's an example of yet another Intel Micron collaboration, where we actually ran the Llama 2, version 2 Llama LLM on the CPU. As you know, in an LLM inference, the subsequent token generation is memory bandwidth intensive. And by using address interleaving technique, we did just that. And we also deployed the onboard Intel AMX accelerator to do the fast matrix multiplication. So once the parameter data was looked up with high bandwidth from the memories, AMX helped to crunch the thing and make the LLM go faster, inference go faster. And here's the 23% performance boost, which we were able to show. And last but not the least, we have the example of in-memory caching database acceleration, which was contributed by our IHP partner, high-radix. They showed off the popular cache-lib in-memory database getting a boost with CXL memory. Now, yes, this is not quite an AI workload, but I still, since I acknowledge so many other IHVs, I also want to acknowledge high-radix here. So that's whole another area, like just simple, some of the in-memory databases can also be accelerated with this technique. And of course, needless to say, HPC workload also get benefited. I think that pretty much brings me to the end of my talk. So I'll summarize, right? So CPUs will play a big role in AI revolution. There are many workloads like RAG databases and even small LLM inferencing, where CPUs can do the job more economically and just good enough without needing a GPU. And then modern CPUs offer many features, like besides the CXL capability, things like accelerators, which can further help with efficient execution of AI workloads. So I'll finish by the call to action that if interested, people should check out the Intel Xeon family, the Burst platform or 6th generation family, and also all those CXL memories I showed from our IHVs. If you're interested in looking at how to boost the AI performance. Thanks for your attention and thanks, members.